So we've been talking refraction. We know as light goes from one medium to another, its speed changes, and thus the angle it makes relative to the normal changes. Snell's law here describes that to us. So in this picture on the left, we have a triangular prism. It's surrounded by air. So we have this laser light coming from the left. It's in air. It enters into this prism. So for each different color, we could draw the normal line, again, making an angle of 90 degrees with the surface. So for this bottom light ray, which is reddish, the theta 1 is bigger than this angle theta 2 between the normal and that refracted light ray, as expected. Similarly, at this second surface for red, just the bottom light ray, the angle gets bigger as it comes back out into the air. So the angle relative to the normal gets bigger as the light comes back out. Similarly, for the yellow, if we draw a normal line, by the way, I can see a little bit of reflection here happening. As far as refraction is concerned, though, this yellow laser makes an angle, some angle theta 1 relative to the normal. There's an angle, a smaller angle, theta 2, while the light is in this prism. And when we reach this other side, if we wanted to use Snell's law over here to look at this right side, we would have a theta 1 and then a theta 2. The theta 2 is bigger because the light is exiting back out into air. It speeds up. When it speeds up, the angle gets bigger. Now, something interesting is happening with this blue. I do see a tiny bit of reflection, but again, we're talking here about refraction. So if I draw for the blue right here, a normal line, that would be our theta 1. Theta 2 would be really small right there. But notice, let me erase this part, at this back surface, there's no blue light coming out. It is completely and totally reflected. It's all reflected inside the prism. We call this total internal reflection. If no light comes out, all of it reflects inside, total internal reflection. Now, by the way, if we follow this blue light through the prism, we get to this far side, and blue light totally comes out. If we were to draw a normal line here, we have this incoming angle, a theta 1, and then this outgoing angle, theta 2. And this theta 2 is bigger as that light goes out, again, because the index of refraction of air, where the light is entering into, is smaller, so the angle gets bigger. So I want to take a minute and talk about this concept of no blue light exiting. So this concept of total internal reflection. Total internal reflection only occurs when N2 is bigger, just kidding, smaller than N1. So if we come back up for blue up here, N1 was the glass, or whatever the prism is made of, N2 was air. Total internal reflection cannot occur if the light is originally in air and going to the prism. And Snell's law up here explains that to us. So I want you to imagine for a second, we're in water. So let's say this is water, and this is air. If I had some sort of flashlight and I was shining this flashlight at the surface, if I draw my normal line, theta 1 I know is going to be smaller than theta 2. Snell's law tells me that because N1 is bigger than N2. If light exits into a medium where the index of refraction is smaller, then the angle it makes with the normal will be bigger. That's what Snell's law up here tells us. Okay, well, I want you to now think, well, what if we increase? Let's make theta 1 bigger. If theta 1 is made bigger, theta 2 also gets bigger for the same reason. Snell's law still totally applies. Let me drag this to the side a little bit. So technically, there should be a point where theta 1 is just the right angle that causes theta 2 to be 90 degrees. We call this the critical angle. If theta 2 is 90 degrees, that means it's not actually leaving the surface. We can say that N1, in this case of water, times sine of theta 1 is equal to N2, which in this case is air, times the sine of 90, but the sine of 90 is 1. The sine of this critical angle, I'm going to use a theta sub c. In this case, we mean the same thing. Theta 1 was this angle that the light ray makes with the normal, with the light in the water. I'm calling it the critical angle because it is specifically the angle that results in that refraction at 90 degrees. The sine of this critical angle is equal to the ratio N2 over N1. So the index of refraction, where the light is headed towards, over the index of refraction, where the light originates. So in this particular example, we would say the sine of theta critical, well, the light was headed to the air, right? Originally, it goes out into the air. It goes out into the air. This is the angle that gives us exactly 90 degrees, hence the critical angle. So N2 is 1, and 1 was water. So this critical angle, if I take the inverse sine of both sides, is 48.8 degrees. This is specific for the water-air interface. The light must be originating in the water and then coming out into the air. What this tells me is if my incoming angle in my picture is 48.8 degrees, then refraction occurs at exactly 90. And so really it will just look like reflection. If my light is any bigger, so if theta 1 is at all bigger than theta critical, it's as if that surface were a perfect mirror. And this is why we call it total internal reflection, because it just reflects completely within that surface. Now, I don't know if you are a scuba diver or snorkeler, or you just like to dive down to the bottom of a swimming pool. What this means is if you are in a pool or a lake and you look up at a surface, you can only see out a certain region, because any light that is hitting at larger than the critical angle will simply reflect. So if you look above you at the surface of the water, it will look as if the surface away from you is a mirror. You don't see out of the water at all. And then there will be a region that you see through and you can see out into the air. Where this really comes into play for us are cables. So our internet. There are thin, tiny little cables such that the light coming in, so the wave coming in, even if it's at an angle, the angle is such that the light just keeps reflecting inside. And so the light waves do not leave the cable. They just continue till they get to the source. I found a little demonstration to show you. This demonstration is to just show you the concept behind these fiber optic cables and the total internal reflection. It's just using water though, but it's still pretty cool to see in my opinion. I have sped it up a little bit just because no one talks. They just show you the setup. So here we go. So this is a jug of water. There's a hole that's covered up right now. So that laser light is just reflecting back and forth within that spout of water. Okay, so just to see total internal reflection, again, total internal reflection only occurs if N2 is less than N1, and it only occurs if the light is hitting the surface relative to the normal at this angle, this critical angle, or larger. The reflection still occurs if that angle is larger than the critical angle.